entered 3016775288.
Oh, it is not working. Okay, I can use, I think, just my my audio here. Hi everybody, can you hear me?
Yes, please.
Yeah, sorry, I ran late in another meeting. So today we are going to talk about the estimator API in TensorFlow. The estimator API is the highest level of abstraction in the TensorFlow API hierarchy, and it helps us to build production-ready models very easily with very few lines of code. But before that, let's see a recap of. Do you have a link to the Zoom? Yes. Yeah, okay. So give me a second here, I'm having some issue. Okay, so last time we talked about what TensorFlow is and why it is called TensorFlow, and we said TensorFlow is an open source high performance numeric computing that represents the computation using DAG, or the directed acyclic graphs. And we said in the DAG, the data or the tensors, where a tensor is n-dimensional n-dimensional data flows through the DAG, and that is why it is called TensorFlow. And we said in TensorFlow there are two modes of execution: eager mode, which is imperative like in Python and R, and the lazy mode or the graph mode, which is recommended for production because it improves performance by reducing the context switches between Python and C++. And also we saw on different TensorFlow functions that we can use in machine learning. One of them is creating a variable. So when we build machine learning models, we create a variable, and as a model learns, it updates the values of the weights. So the weights are initially created as variables with some initial values, and usually we initialize them using truncated normal. So if you go to the TensorFlow documentation, under TF initializers, there are different ways to initialize a variable, and truncated normal is one way. Actually, there are also other under the tf.keras API, there are other initializers that converge quickly and also are proven to give better performance. And the other one was about creating a placeholder. So when we create the DAG, what we do is we create a placeholder, and then we pass data during training. So that is also another important thing. Creating variables and creating placeholders are among the important things we saw last time. So today let's talk about how we create models using pre-made models using the estimator API, and also why the estimator API is important for productionizing models. So if last time we saw this TensorFlow API hierarchy, we said you cannot see it.
No, I can't find the link.
Oh, yeah, sorry.
This thing is here. Oh. Do you mind?
No problem. Yeah, but it is not working for me. Can you try? Okay. Yeah, last time it worked with. Yeah. Oh, thank you so much. Yeah. Okay. So in this TensorFlow API hierarchy, last time we used the core Python TensorFlow, and also we said we can create a custom neural networks using this layer, the TF layers, TF losses, and TF metrics. But if we create our own custom neural network, productionizing it running it in a distributed fashion, and checkpointing or monitoring its performance is not easy. Whereas the TF estimator, it handles all these things for us. Like we can run it in a distributed environment, and we can also run, as the model runs, we can save the outputs and monitor its performance, how it is performing, and also it is easy to deploy it in production and hence use it for inference or prediction. So using the TF estimator, it helps us from writing lots of code, many lines of code, especially if you want to try different models. There are pre-made models. We can try different of them without the need to write many lines of code. So as I said, this slide shows the different advantages of the estimator API. We can easily try different models. We don't need, if you try one kind of model and you wrote code for that model, and if you want to try another one, if you are creating the code yourself, you have to still write many lines of code. You have to make many changes. But with the estimator API, you just change the model name and also probably some hyperparameters that are appropriate for that model. So you can easily try different models from that perspective. And as I said, also checkpointing is also easy with the estimator. So you can visualize the model performance in TensorFlow, TensorBoard. And also the other thing is we don't always build models using data in memory. Like we may need to train models on large data sets out of memory by loading gradually. So out of memory data sets, using the dataset API, we can also build models using out of memory datasets. Like if you have large amount of data, the estimator API is also handy from that perspective. And the other advantage is in Cloud ML, using the estimator API. Once we build the model, we can use Cloud ML and tune the different hyperparameters. We pass a list of different hyperparameters, and yes, it fits the models with the different hyperparameters that we provide and gives us the best model with the best results. Distributed training is also another thing which is required, especially when we are working with large data sets. And finally is productionizing it. So what are the different pre-made estimators that can be used from TF estimator? So under the TF estimator API, we have different pre-made models. So the first thing is TF estimator.estimator. This one helps us, if we build our own model, we can wrap it using TF estimator.estimator so that we get advantages of TF estimator. If you create your own model and you wrap it using this, then you can do the distributed training, hyperparameter tuning, checkpointing, and everything, monitoring and serving. And the different pre-made, there are different pre-made models also. So those that end with regressor, that means they are used for numeric value, like the level or the output is a continuous numeric value. So it is a regression. Whereas those that end with classifier, they are categorical outputs. They can be binary or multi-class classifier. So here we have baseline regressor. This one, it creates a baseline. So what it does is, if you have numeric data, it just takes the mean. This helps you to, once you create the baseline, it helps you to compare with other models that you are building, basically. And we have linear regressor, DNN regressor, deep neural networks regressor, DNN linear combined regressor. This one is also called wide and deep regressor. This is common in enterprise machine learning, and it powers Google Play recommendation engine. So what it does is, for the numeric values, since there could be nonlinear relationships with the output, it uses neural network. Whereas for the categorical values could be simple boundary lines, so it uses linear model in that case. So it combines both the linear model and the neural network. and it has also boost tree regressor. These are the regressors for continuous data when we are using the regression. And for classifiers, we have here baseline classifier. So this one, it just calculates the probability. If you have, for example, binary outputs, it just calculates the probability. We have linear regressor, DNN classifier, and DNN linear combined classifier, and boosted tree classifier. Actually, the boosted tree classifier, for now, it works only with binary data. It doesn't work with multi-class data. It is the same also with Spark. Spark ML, boosted tree, it works with binary classification only at this time. I don't know why. Okay, so let's see how to build a model using an example. So this slide, what it shows is let's predict house price using a couple of different features. So the features are the predictors or the variables that help us to predict the output or the predicand. So in our case, let's consider square footage and the category of the house. Is it an apartment or a house? So to build a model in TensorFlow, it is slightly different from what we do in scikit-learn, in Spark, or in R. So the first thing we do is define feature columns. Okay, the feature columns. I mean, we identify the variables first, but also we use an API called feature columns. The feature columns, what it does is it makes the data in a format that TF estimator can understand. So it is a bridge between TF estimator and the raw data. So first we define feature columns, then we define input functions, then we instantiate an estimator like the DNN regressor or the DNN classifier, then we train, evaluate, and predict. So in here, if you want to understand the different the use of feature columns, you can read this. So it outlines different types of feature columns and what feature columns are, what actually TensorFlow is doing with it. And
Question.
sure.
How does this integrate with TF extended?
TF extended, I'm not sure I know it. So it helps to extend your custom model?
Yeah, so basically in terms of distributed feature extraction, my understanding is, so TF extended, you can do the same pre-processing with Apache Beam.
No, okay.
With DataFlow actually, and then I'm not sure how this works, but presumably if you do some kind of feature scaling and so on, which is what this feature columns would do, right?
Yes.
Then you can, after you compute these features, maybe write them to a TF record file and then do distributed training with them. You could then package it as part of the graph. Yeah.
Oh, I see. So
hey Fish, we don't hear Daniel's voice clearly. Would you be able to repeat the question for us?
sure, yeah. So what he said is how is this related, or how is this similar or different from TF extended? And yeah, I have never used TF extended, and we didn't also cover it in the immersive training. So I don't know actually what it is. And the other thing with TensorFlow is there are different APIs that do the same thing, because it is open source. So many people contribute more or less similar things, and they said in TensorFlow too it will be like normalized. Only one function will be available to do one thing. So probably the things that TF extended does can be done by the other functions that we are going to cover here. Yeah, so we can go to the documentation is very important, by the way. So in TensorFlow, it is different from scikit-learn again. I mean, the function name is very long, so you have to always be consulting the documentation. So let's first see the tf.estimator from the documentation, if you can see it here. So we have the different kinds of pre-made models. all the DNN and linear or linear and DNN combination models you can see here. And for one model, if I want, for example, DNN classifier, just click it and you go to here to init to see its arguments. If I press here, it gives me what the arguments are, which ones are required and which ones have default values. In this case, for example, for the DNN classifier, I need only the hidden units and feature columns. But for the others, there are default values, and the default values usually work fine. But if you want to fine-tune your model and compare different results from different parameters, you can change them and try different results. Okay. So how does the feature column? How is the feature column to be used? So what we do is, first we create a list of the feature columns. How do we do it? So here, once we import TensorFlow as TF, nice. Well, I don't know where my cursor is. So here we imported TensorFlow as TF. Then we are creating list of the features. But the features, it should not simply be name of the feature columns. It should also specify what type of column it is. For example, if it is numeric, we use tf.featureColumn.numeric column, then the column name, square footage in our case. If it is categorical, and if the category is small, we can use tf feature column, categorical column with vocabulary list. Then we write the column name and pass the possible values. Like in our case, house and apartment. If we have 3-4 values, we can manually write them. But if we have many values, there is tf feature column, categorical column with vocabulary from file or something that we can check from the documentation. So once we create the feature columns this way, then we instantiate the model. And when we instantiate the model, we pass the list of feature columns we created. Okay, so TF feature column, it handles different kinds of columns based on the data that we are using. So far we have seen categorical column with vocabulary list. If you have to manually pass a list of the categories, if you have a file of the lists, if you have, for example, if you are considering zip code and you have 30,000 zip code, you cannot manually put them. So you save a file of distinct zip codes and you can pass that. And categorical column with identity, like if you have numeric column but the numbers actually don't mean anything, like for example, if I have days of week from 0 to 6, in that case I have to change them to categorical column with identity, and so on. So you can explore this. There is also embedding column. If you have text, you can embed it. That means when we embed it, it means it is like clustering numerical values. What it is doing is it is creating a lower dimensional representation of the text.
Is it word2vec or is it using Flow?
I think it has both options, but I'm not sure. In the arguments we can check. And also, if you are not familiar, there is this crossed column. So feature crossing is it is not common in the kind of traditional machine learning. When you are working with small data set, actually we call it feature engineering. So feature crossing means by combining features you create a new feature, like by multiplying. For example, if you have a circle, and for example, if you have a circle and if you use xy for your model, your xy will not do anything. The model cannot predict, cannot classify. If you have different circles, it cannot classify which points are in the circle and which points are outside of the circle.
So like interaction terms.
Yes, they are interaction terms. If you consider x square, y square, or x and y, the other thing is different colors. Car colors could be used in America and in Europe, for example. So you multiply two columns and create an additional column. That is called feature crossing, and it is very important in deep learning. Okay, so yeah, so what is the feature column API doing? Let's quickly see that. So when we create a linear model, the model, it is learning weights, right? So you have some input, and by multiplying using the weights, it is giving us an output. If it is numeric column, it will be used as is. But if it is categorical column, the TF feature column categorical column with vocabulary list or with category from file, it is doing basically one hot encoding. So one hot encoding, what is it? Like if it is a house, I have a house here. If it is a house, it will be 1 0. If it is an apartment, it will be 0 1. If you have a served category, it will be 0 0 1, and so on. So once it creates such kind of one hot encoding, then the model can learn the weights, update the weights, and give us a prediction. And as I showed in the previous slide, there are different ways to create feature columns. This one is an example. Okay, before I show this one, let me quickly show another thing. So, okay, exit. Okay, so list compression is very, very handy when we create feature columns in this case. And let me quickly show what list compression is in this case. So list compression, if anyone is not familiar with list compression in Python, what we are doing is, if for example, let's say we have list of numbers here, range 11, it creates a list from 0 to 10, excluding the last one. Then from these numbers, let's see which ones are even and return square of those even numbers.
Where are you?
Oh, okay. Let me increase the font.
No. Like what?
Oh.
What environment is this? Like a Jupyter notebook?
Yes. Yeah, this is Jupyter Lab. So Jupyter Lab is very nice. So if you go here, it gives you here. There are different things. You can clone from GitHub and push to GitHub. It supports different things. Upload file. It is different from the.
But is it running off your computer? I see
yes.
localhost. Okay.
Yes. I just wanted to show list compression and stuff, and then to show how you can use list compression to create feature columns. Because in deep learning, you are throwing as many features as you want, and you cannot manually creating the feature columns manually is time consuming, and also you could be prone to errors. So using list compression is handy. So what I'm doing here is, I have a list here. I want to get square of the even numbers. If you use a for loop, it becomes like this. This is many lines of code. But if it is list compression, if you follow here, what I'm doing is I create a list here with a square bracket, and let's call the even. So this list, initially the list of the numbers, we call them numbers. And let's call a given number. So if that number, the modulo of that number, if the modulo of that number is 0, that means it is even. So give me square of it. When I just do this, it gives me the same results as a for loop. So list compression is very, very handy, especially when you are using Spark with Python and also TensorFlow. It is very handy. So in our project, for example, we have 400 columns, and out of the 400 columns, about 397 of them are numeric, and we have a way to identify which ones are numeric. So first, we create the column names. Just use the quotation here and at the end, and split it in comma, rather than creating a list of the column names where you have to put every one of them as a string, which takes time. Then after that, and when we are pre-processing the data for the numeric columns, we put C, like we have this C first. So in here, we can extract the numeric columns. What we are doing is, if this pattern is available in call, then that is a numeric column, so give it back to me. So I call it numeric column. And also there are other also which are not captured by this pattern. So also these ones we have added. once we identify the memory column, rather than creating one by one as I showed in the slides, just we use only this one, the last one. So now I can get back to the slides and okay. So here okay. So here, as I said, we have 397 memory columns, but we just wrote only one line to create the feature columns. tf.feature column, memory column, key is k, for k is in memory columns. So k is in this list. In this list, we have 397, and all of them, all of the list of feature columns, we can create it using this list compression. And once we create this for the memory columns, for the other columns also, if there is a way that we can use list compression, we do that, or we create them one by one, and finally we create a list of all the feature columns we have. So list compression is very important, is the point here. Okay, yeah, I have to be quicker. So let's see, like for example, with dummy data, how we do that. First, we write we write functions for the training input function, validation input function, and testing input function. So first, this shows the training input function. In the training input function, the data, how it should be represented is like as a dictionary of key values, where the keys are the features and the values, list of values. So square footage and the type we have as features, and the level also. During training, we need the level during training and validation. So that is why we see the level here. And then once we have this, once we instantiate this function, we instantiate the model, then model.train, where the train input function is what we have defined here, and also we specify the number of steps. Number of steps here is like, so the machine learning model, what it is doing is initially it is starting with some random weights, but it has to be rerun. It has to run a couple of times using a master algorithm called gradient backpropagation to improve the weights. So we can specify the number of steps we want, which depends on the complexity of the model and also other factors. And for prediction, during prediction, actually we don't have the level, we have only the data, the features. So the same thing, we create a function for that. So we have predict input function here with square footage and type, and we can make predictions. So the model that predict, it returns a Python generator. So that generator, by using next, we can see what it has predicted, for example. So general, yeah, this one shows all of them together, I think. We instantiate the model, tf.estimator, linear regressor, we pass the feature columns, then we train a model, and then we make predictions with it. So this is a linear regressor. And what are we doing with neural network? With neural network, basically we are learning the thickness of the lines here. So the input layer contains the different features, whereas the hidden layers, like there are some multiplications of the weights or the lines, the line thickness with the values from the input layer. So that is what it is learning. And the hidden layer, we can have as many hidden layers as we want based on the type of complexity we want to create. So it is learning this kind of weights, and we have to specify how many hidden layers and the number of nodes we want in each layer. So in the previous slide, in this one, we used TF estimator linear regressor. That is why we didn't need to pass any required parameter arguments. Whereas in DNA regressor, we have to pass the hidden units. So the hidden units are.
Sorry, would you please exit this slide mode? The slides become very small.
Okay. Oh, I see. Yeah. Okay. Is it better now?
Yes.
Oh,
Thank you.
I see. Okay. Yeah, we're projecting it, and I thought that was being projected. Okay, so in here, once we create the feature columns, let's say we tried the linear model, linear regressor, and it didn't work fine, it didn't work well, and we want to try another model. We just can try from the pre-made models. Now we are taking the DNA regressor. The only thing we need to specify here is the hidden units. That's the only required argument. The feature columns, we created them in the previous slides. Had this been creating your own custom model, you would have to write lots of lines for the linear model and then another lots of lines for this one. So the TF estimator is very handy from this perspective. Even when you are building model with small size data, still it helps you to create to try out different models. And yeah, so we have here, it shows the different parameters that we can specify. You can see the documentation, but most of the time the default values are nice. In this case, we are specifying the dropout, the activation function, and the optimizer. You can read about the different activation functions from the documentation, but dropout is a regularization technique. So what it does is from the different connections, it randomly drops some of them down, like it multiplies them by 0, changes them to 0, something like this. So this is like a regularization technique. When we say regularization, the model, so if we train the model for lots of times, then the model, rather than learning some kind of mapping, it may memorize every detail about the training data, and in that case, when we try to make predictions with unseen data, the model will do a bad job. So
this is called overfitting, by the way.
Yeah, so in this case, we want the model to generalize. It should learn some kind of robust mathematical mapping. So dropout is one technique, and usually from these connections we drop like about 10 or 15% of them. And also in here, the other thing is optimizer. Here it uses Adam optimizer. There are different optimizer techniques, and those optimizer techniques, what they are doing is, so initially when you the weights are what you need from your machine learning. The weights are what you are learning, but initially you initialize them randomly, so you will get a very bad model where the error is very big. So you have to minimize that error. So in this case, we are minimizing that error through iteration. So initially it was here, and there are different techniques that go downhill and find the minimum value for the loss that we are optimizing. So in that case, when I reach here, that means my model is good and my model performance is nice. And there are different functions that we can optimize. When we have regression or continuous numbers, we optimize the loss is a mean square error, which is the difference between the predicted and actual values squared and average of that. If it is classification, we have what is called cross entropy. You can read about them. And as I say, the TensorFlow documentation is very important. Like if you go to the TF-Keras API, you can see the different optimizers here. We just saw this one, Adam. The different regularization techniques are here, and also activation. There are different activation techniques. So the activation technique, what it is doing is, here we have the inputs from the feature columns. They are being multiplied by the weights, but once they get here, they should be transformed using some non-linear kind of mathematical transformation. Otherwise, all this will collapse and it will be a linear model. So there are these activation functions transform the data and help us to get to represent non-linear relationships between the input data and the output. So, and the other concept is checkpointing. Checkpointing is important with TensorFlow. So if you are training with big data, you can resume from where you stopped. So in checkpointing, it saves the weights that it has learned so far in a given directory, and next time when it starts, it continues from that. That is called checkpointing. Also, it helps to resume on failure. And something which is not common is other machine learning tools is getting model performance, different metrics on the TensorBoard. This is coming from checkpointing, because every time it is saving the weights, even if the model is running from the weights you have so far, it can give you what the evaluation metric looks like. Is it improving as you run more steps? And when you run more steps, if it is not improving, then you decide whether you have to wait more and see if it has to improve, or if your model has to be changed and so on.
So basically, picture like real-time training status. Like,
right.
It's pretty sweet.
Yeah. So yeah, I had more slides for today, but because I came late, I could not cover more than this. It is 1 p.m. already. So we'll continue from here next week. So from now on, it will be more fun. We are working on the actual modeling efforts. So yeah, and thank you very much. Thank you, everyone.